All right, I guess I missed the last question here. It's number 5, and it's using the same sort of information we've been using so far. So remembering that our formula is F is equal to ma. So it says a vehicle with a mass. So I'm just going to write that down up here. Our mass is 1250 kilograms. Travels at an average velocity of 45 kilometers an hour. East. Should probably put that part. When the driver engages the brake to stop at an intersection. Okay. So this is our, I guess, initial velocity. Our final velocity is going to be 0 because they're going to stop. It says if the net force applied to the brakes is, so our force is equal to 7,000 newtons west. Determine the vehicle's rate of deceleration. So deceleration is acceleration as well. So this is quite the question. So A is asking us to figure out what the acceleration is. And we can do that using F is equal to ma. There's a lot of other information there, and that might have to help us do question or letter B, but we will see when we get there. So it says F is equal to ma. We're going to use that formula rearranged, which I should have rearranged it before I wrote it. Rearranged would be A is equal to F divided by m. So to do that, we were going to get 7,000 newtons divided by our mass, which in this case is 1250 kilograms. So if we calculate that on our calculator, we should get the deceleration that is happening here. And something to note, when we were talking about deceleration is normally a negative number. And I guess that makes sense because west, which is right here, would translate to being negative if we're not going to put west in there. So this number will be negative, and I got this silly calculator that gives me fractions. So if we do that, we get 5.6. Okay, out as a decimal, and that's acceleration, so that's in meters per second squared. Okay. That's fine for significant digits, really, because 45 would be our lowest. Let's do B, though. So it says determine the length of time that this net force must be applied in order for the vehicle to come to a complete stop. So we're looking for a time. We've got some pieces of information that we can use. And the formula that we're going to use to figure that out is acceleration. Or I think that's the formula I would use here. Okay, I'm going to use that formula rearranged so that we're solving for time. So time is equal to, V divided by A. Okay, just had to figure that out. So that's the formula we will use for this. We're going to figure out time. We've got a velocity. Our velocity here is 45 kilometers an hour. And we've got an acceleration, which is 5.6 meters per second squared. So there's something majorly wrong here, and that's the fact that this is in meters per second squared and this is in kilometers per hour. So we're going to actually have to change that. And to change it, I'm going to change the velocity into meters per second. Does the question tell you which way? It doesn't, but we're going to do that. So this is where we're going to be using those conversions. I'm just going to do it down here. So 45 kilometers an hour. We've got kilometers, hours, seconds, meters, 1,000, 3,600, 1, and 1. So if we calculate that, we go 45 times 1,000 divided by 3,600 will give us, again, a fraction, 12.5. And that's meters per second. Okay, so now we can sub in that for the velocity. So the velocity is not 45 kilometers an hour anymore. I'm going to get rid of that. It's actually 12.5 meters per second. So now that I have that, I can calculate this question. So my time is going to equal to my velocity, which is 12.5 meters per second, divided by our acceleration, which is 5.6 meters per second squared. Okay, so when we do that out on our calculator, we should get our answer. And I figured that out to be 2.23, and that would be seconds. So the question asks us, determine the length of time that the net force must be applied in order for the vehicle to come to a complete stop. So when you're going 45 kilometers an hour, I guess putting your brake on will only take 2.23 seconds to come to a stop. That seems pretty fast, but I think we've done the math correctly, so it should be right. All right, so that's how we do a question like that. So Newton's first law of motion, it says, in the absence of a net force, an object in motion will maintain its velocity, and an object at rest will remain at rest. So that's the classic, an object in motion stays in motion. This is referred to as Newton's first law of motion. Newton's first law explains why a space probe requires no engine to travel beyond the solar system. In deep space, there's no friction to slow things down, so the probe simply maintains its initial velocity. So something can maintain and continue to move as long as it doesn't lose its energy, mostly to friction, which is normally why we come to a stop eventually. So an example here, it says a car with a mass of 1,075 kilograms. So this would be a mass. Is traveling on the highway. The engine of the car applies a force of this. So we've got a force of 4,800 newtons west. So that's negative. To overcome the frictional force of 4,800 newtons east, so that's a positive. What is the net force applied to the car? So your net force is basically adding your forces together. So if we go negative 4,800 plus 4,800 newtons, we will get 0. So the net force, there's no 0 for our net force. Determine the car's rate of acceleration. Will it speed up, slow down, stop moving, or continue moving at a constant velocity? So we know it shouldn't continue at a constant velocity because there's force of friction there. If those forces are balanced, remember that something isn't moving. So if there's just as much friction as there is in the engine, then it's not going to move. There'll be a 0 net force. So figuring out the acceleration here. We would go force is equal to acceleration is equal to F divided by M, and in this case our force is 0 divided by our mass, which we know is 1075. So So regardless of this, this 0 is going to tell us that our acceleration is 0. And in knowing that, that means we're not speeding up, definitely. And because we don't have any force, we're going to assume, or no net force, then we are not moving, we're stopped. Okay. Gonna stop there for